You're all quiet, usually quiet anyway. So, all right, officially, hi folks, welcome back. So I thought I would start with reminders of what you're working on. So nothing was due yesterday. Homework 2 is due next week, and then we have spring break. We're almost to the halfway points, which I find very unable to believe, but somehow that's what's happening. So that is always an exciting midpoint. Anyone going anywhere interesting? Zoomers? Any interesting spring break plans? You want to make the rest of us jealous? I'm going to Omaha. Woo! Maybe Colorado? Okay, I'll take that. Staying here, yeah. Yeah, I usually don't go anywhere. We're just visiting my family and for my son's birthday. Playing Animal Crossing? Oh, that's nice. That takes me back to the pandemic. My son was addicted to Animal Crossing, and he was only 5, so he couldn't read yet. So my entire job during the pandemic was to sit next to him and read the captions so that he could decide what to do. It was very, very motivating for me to help him learn to read. Let's put it that way. But my son Hugh will make an indirect special guest appearance in this lecture, by the way. So you'll know it when you see it. I'll just say it that much. But what you have to work on then, before spring break, is homework 2 due next week. And I've heard from the TAs a couple common points of questions, so I thought that might be useful to go over as a group, and then I can entertain questions. So in terms of, let's see here, in section 1, you can use whichever software you want to answer these questions. This is based off of example 3, so you have code that would get these for you in every case. The only catch is this one right here. I'm asking you to do a separate calculation based on the obtained alpha, what the average inter-item correlation must have been. And here's exactly where you can find the formula. I just double checked and it is indeed right. So then based on that formula, you can find the average inter-item correlation. And then number 10 is directly related. Given that correlation, what is average shared variance? What does this phrase mean right here? How does that relate to correlation, the idea of shared variance? R squared, yes. So looking to reinforce that concept that R squared is R squared, because that shows up as measures of effect size. Yes, R squared, thank you, Zoomers. And section 2, there's 2 different ways to do this. What I had specified in the instructions is to use M+ and provide the option type equals basic. There is an example of code that looks like that inside here. So the link to the example files that I initially used to demonstrate how to access M+ and make it go, there's a model that has type equals basic in there that you can use and adapt to make your homework go. Alternatively, you can fit the saturated model. So there's an example of that within example 4 specifically. The saturated model is when you estimate all possible means, variances, and covariances among your items, and then that will be able to allow you to answer these questions. If you try to use descriptive statistics, like if you run summary in Stata or what is it called? Describe in R, something like that, you will not get the right answer for the variance and covariance because those versions divide by n-1 rather than divide by n. So you can do the algebra to rearrange it, but I had intended for you to get these statistics out of the saturated model or the descriptive model that is provided when you just do type equals basic. So I've answered a couple questions on that. So any questions from everyone here on 1 or 2 sections? All right. Then section 3, note the bold face here for signed difference. So I'm looking for you to recognize when your fit statistics are lower than they should be versus higher than they should be. That's what I mean by signed. And let's see. Yeah, so most of this is fairly straightforward. Note that within the instructions, I'm telling you how to identify the model and any other notes about what should happen and what you should do. Any questions on section 3 that I can answer right now? Zoomers? moving on. Section 4 then, just had a discussion about this with the TAs. So question 50 and 51 here are yoked together. Note that section 4 requires completing 3 different models. I would highly encourage you to save the outputs from each as separate files to refer to. That way you can answer all of the questions outside of M+, on your own time. But question 50 is asking about the largest normalized residual for covariance. So in this context, residual means discrepancy. It's the difference between what the model says the covariance between 2 items should be and what the data say. And I'm asking for the largest one out of all the possible combinations, and then looking for you to modify the model to introduce a new parameter that would solve this problem. So the 2 items that have the largest residual, I'm asking you to add an error covariance between those 2 items. And you have examples in your code of how to make a covariance. It's the keyword with. It doesn't matter if it's a covariance between factors or a covariance between errors, it's still with. All right. That. Okay. Any questions on section 4? No? All right. Then I'll just ask you again on Thursday. And if no one has started it by Thursday, then you'll just all have lots of fun this weekend. How's that sound? All right. Fair enough. Okay. I'll shut that off then. We have a new topic to talk about today. So this is the point of intersection of the 2 classes that I am teaching this semester, and why I had strongly recommend that for this unit, you should familiarize yourself with regression models for predicting binary or categorical outcomes, because that is exactly the same technology that we're going to be using to fit factor models that predict binary and categorical outcomes. Starting with binary for right now. This lecture used to be over 90 slides, and I decided to cut it in half for the same reason. So it's 56 slides. We're not going to do them all today. I don't know how long it's going to take, but it's going to take as long as it takes. How's that sound? Yeah. So this is the unit that I think differentiates the way that I teach this class and the way that Jonathan has taught this class in the past from other more traditional SEM classes. Most of the time they start with path analysis and then go through CFA and then jump into SEM. But as most of you have seen with your own data, is it likely that the items you're going to analyze are continuously distributed? Nope. Like, no one has that. Even folks who have somewhat continuous data that's not ordinal still has boundaries, like proportions bounded between 0 and 1. See, I warned you. You did. So most of us have binary or ordinal response formats. And so the models that are for continuous responses instead are going to be, best case scenario is a good enough approximation. But these models are designed specifically to predict binary and categorical outcomes. And so because most of us have that kind of data in the social sciences, I wanted to put it in here. So that's the big picture. We have a little bit of review and then an introduction to what are known as item response theory models. And the second half of this is going to show you the translation into something that looks a lot more like factor analysis, as well as a little bit about estimation for these things, because that's a whole story unto itself. So, are we ready? Why not? So, big picture stuff first then, and away we go. Zoomers, am I still good with the microphone? Not screechy, not coming in and out? Okay, if that changes, please let me know. But as I said at the top of the hour, I have a new connector. So I'm hopeful that that has solved the microphone problems. And I'll just peek over at my recorder and make sure that it's still listening to me talk. Okay, looks like we're all good. All right, away we go. So, big picture, where we've been up to this point, we started with the world of classical test theory. Basically, to me, that is the set of logic and assumptions that allows you to add or average a series of items and think that that is your best way of describing a person's standing on a latent construct. So there's all kinds of formulas and whatnot by which we can try to quantify reliability and all of that kind of stuff. The key thing that I want you to take away with respect to how that fits into this class is the idea that the model does not have anything about the items in it. The classical test theory equation is that your total, the sum across the items, or the mean, doesn't really matter, is a function of each subject standing on the latent trait, or what is known as true score, plus some amount of error. And because the items aren't in the model, we have to assume they're exchangeable. We don't have anything in here that would keep track of how difficult they are, how discriminating they are. So the sum score serves as the latent trait estimate, which means that you can't interpret those latent trait estimates without referring explicitly to the items from which it came. So the item difficulty, index of item difficulty in classical test theory is the mean of the item. So the mean on a continuous item or the proportion of ones on binary items, that's sample dependent. Likewise, item discrimination is indexed with the item remainder correlation, the correlation of each item response, with the total omitting that item, and that's also a sample dependent property. And to be able to quantify reliability in these models, we would assume without testing unidimensionality. That's the biggest one. If you don't have that, everything is going to be way off. If you also are willing to assume tau equivalence, that leads to alpha as a measure of reliability. Instead, if you want to assume parallel items, that leads to the Spearman-Brown formula as your index of reliability. Do you remember the difference between these latter two? What's tau equivalent versus parallel? Tau equivalent, also true score equivalent. Erica, I'm going to call on you. She's given a big talk on Friday all about this in our ProSem.
The parallel items has to have the same discrimination and the same, the errors have to be the same.
Error variances. Yep, parallel is same discrimination and same error variances.
Whereas with tau equivalent, I believe the error variances can differ.
Yes, with tau equivalent, the error variances can still differ. The discriminations are the same. And that was like the last thing we did, I want to say last week, maybe? How did we actually test this within a model? Do you remember that? They had labels in parentheses. Remember? She's still nodding, go for it.
You constrain them to all be the same. So you only give it like one label instead of like the 6 of another.
Yeah, so if I have 6 items, rather than giving the loadings 6 different labels, I would use one label, and that makes the single loading hold across all of the items. And then what? What do I do to see if that's okay?
You compare it to the model that has the 6 loadings and see with the likelihood ratio test whether or not it's significantly better or worse.
Yes, so I would use a likelihood ratio test, so compare the differences in heights for a model in which all the items get their own slope loading versus a model in which they're constrained to be the same. And if they fit differently, that means the constrained loading is worse or the 6 separate loadings is better, however you want to talk about it. And we can do the same thing with the items. So we have several indices of model fit that would tell us if unidimensionality holds, or to the extent to which it holds is probably a more fair way to say that. Then we have these potentially nested models that we can estimate to see if these things further hold. So it's just a question then of what your data say. If they don't want their loadings constrained, then alpha is not going to be the right measure of reliability, and we would do something else. Do you remember which one it is? Starts with an O? Omega. Yeah, both of those are indices of sum score reliability. We could also compute factor score reliability in that case. And omega uses the differences in the loadings and the differences in the error variances, as well as any error covariances. So, point of the story though, each of these is one number, right? We would have a value for omega, a value for alpha, or a value for Spearman-Brown. That means that we are assuming that reliability holds across the trait. So what kind of instrument, how do I make my instrument better according to classical test theory? I need more items. More items will make my alpha higher. It will make my Spearman-Brown reliability higher. It will indirectly make omega higher. But what kind of items? Just more. More is better, because items aren't part of the story here. So then we moved on to CFA, and I think I have one. Double check on the recording. Zoomers cannot see the recording icon on our end. That is because I have a separate piece of software running that records this. That way it's not tied to Zoom, and the software is not recording anything about the Zoomers. or the rumors for that matter, just your audio. So that recording, I'm double checking again, is still going. So I believe we should be in good shape. But thank you for the prompt. All right, so questions so far? No comments. Okay. Then, where we just finished, CFA stands for confirmatory factor analysis. Here, the items are part of the story. So now each item gets two properties. It gets an intercept, which is an index of item difficulty, although it's backwards, because if an item has a higher intercept, then at a trait score of 0, it has a higher expected response, meaning that it's actually easier or less severe. So conceptually, it's backwards, but we still call it difficulty. And this is sample independent because it's breaking the tie of persons and items. The intercept is conditional on a factor score of 0. So that property should hold across different samples. As long as you have people in your sample that have a factor score of 0, this is their expected response. And you can figure out what the expected response would be at any factor score, regardless of what sample you're in. Likewise, our factor loading here is our index of discrimination. That's lambda, and that is a slope. It's the change in the item response for a 1 unit higher of the factor score. And this is an index of discrimination where more is better. So these slopes are linear. That's one of the big things to keep in mind. A linear slope means that the change in y per unit change in x just keeps going forever and ever and ever. It doesn't, there's no boundaries implied by that model. And that's why this is less than ideal for ordinal data. Responses are supposed to be uncorrelated after you control for the factors. However, if they're not, we can fix it. So can you think of a couple different ways of addressing unintended multidimensionality? Such as one on the slide here. Zoomers, want to read from the slide? Anyone?
Is that when you like just add that extra covariance?
Yep. Yeah, we got the gesture here because it looks like a two-headed arrow usually. So a covariance between the errors literally plugs the hole in the discrepancy matrix where you're off between what the model wants and what the data say. So you can add a correlation to solve that problem. What else could you do? What do we do in example 4? Single factor didn't fit. I made 2 factors because I decided a second factor was a more reasonable way to proceed than a whole bunch of error covariances. So it's a principled way based on the wording. One factor was measuring forgiveness, the other was measuring not unforgiveness in that case. What if I really don't want to have a second factor, but I got to fix this?
Is it the bifactor model?
Yeah, the bifactor or method factor. That's the one where after you have all of the items loading on one factor, you create a second one that's uncorrelated, and then you have just the items that you want an additional relationship to load on that one. So that one is like a broom, just to sort of sweep it all away. People usually try to disregard it. All items are initially loading on the factor that you had intended. That bifactor / method factor approach is going to be the only way to do it when we have IRT models estimated with full information maximum likelihood. There is no such thing as error covariances in those models. Okay. So because the item responses are included, we're no longer assuming that items are equally discriminating. We can actually test that with the likelihood ratio test. And if they need to have different loadings, so be it. Then we would use omega, for instance, if we wanted an index of reliability for our sum score. And items also vary in difficulty via the intercept, but we don't really care about that in CFA. So if I wanted to make my instrument better, not only do I need more items, but I need more better items. I need items that have stronger loadings. And indeed, if you have an instrument that's very long and you wanted to make a short form, according to CFA, all you would need to look at is the loadings. You pick the loadings that are the highest, the end. Ideally, you would look at the content too, but from a psychometric point of view, just the loadings is all you need to know. And because we still have this idea of constant reliability, constant information, a new term that we're going to be dealing with more, that means that error is considered constant. So we're assuming that everybody is equally well measured no matter where they are on the trait in these models. And that is probably not going to be the case, specifically especially when your items aren't really continuous. Okay, there. Questions or comments about CFA? All right, moving on. So some framing is required here. The analogy that I want to be in your heads as we go through this is the tie between factor analysis and regression. This CFA model looks like a regression model. If it were written to predict observed variables, then my mu intercept would be beta 0. The lambda would probably be beta 1. F would be an observed predictor. So if we look at it from that point of view, I would say that linear regression, meaning that we are predicting continuous outcomes directly, is analogous to confirmatory factor models. That means that if we have some other kind of outcome that's not continuous, discrete, or categorical, what we would call generalized linear models, where ized means some kind of not normal conditional distribution, then we need a different kind of regression. So it's called logistic or probit if it's predicting a binary outcome. It's called multinomial, ordinal, or nominal, depending on who you read, if you're predicting something that's categorical. So the direct translation using this analogy of regression leads us to, if you add a latent predictor instead, we call that either item response theory, abbreviated IRT, or item factor analysis, abbreviated IFA. Okay, so that's the big picture. If you understand logistic regression, the rest of this is very straightforward. If you don't understand logistic regression, this is impossible. I've mentioned this several times, but I'll say it again. I went through my entire IRT class as a second-year graduate student not knowing what the hell a logit was. It did not go well. I couldn't hang on to anything because I didn't understand what was being predicted, and all of the models looked so very different to what I was used to. When I was a postdoc, I had the opportunity to sit in on several classes at Penn State where they had some excellent instructors, and they taught logistic regression in one of those classes, and then they taught ordinal regression right afterwards. And I just sat there in the back going, oh my God, this is IRT. Like, I get it now. So I want to save you like the 5 years in between where I was trying to figure out what the hell a logit is and just tell you what it is, because then the rest of this will go much more easily. And if you're like, I know what a logit is, Lisa, you told me this last year, or you told me this last week, then, go ahead and check your email or whatever you need to do to stay awake. But I need to go over this so that we're all on reasonably enough the same page. And the material that I'm pulling this from is from the previous class. So the unit that we're just wrapping up in generalized is what I want to review briefly in this context. So the idea of a generalized model. We have the same type of predictive model as usual. We're going to have intercepts and we're going to have slopes. The new part are these two pieces here. We introduce the idea of a link function. A link function is a transformation, but it's not a transformation of data. It's a transformation of the mean to be predicted of the outcome. I'll give you an example of what that would look like in just a second. The other piece that's different is that we are no longer forced to assume that residuals have a normal distribution that has constant variance. We can switch out the normal distribution for one that better matches the distribution of the data. And there are combinations of link functions and distributions that work for all different kinds of not normal outcomes. So that's what the generalized class is about. I'm just going to talk about binary for right now. So let's say that we have a binary outcome, meaning it's 0 or 1. In that case, if I know nothing else about a person, what's my best guess for their outcome? Like, where does a prediction model start as the most naive place to begin?
0.5?
Say it again?
Would it be 0.5?
0.5 would be if the variable were equally distributed. But on that same idea, let's say that I know that 30% of my sample has a 0 and 70% has a 1. What's my best guess for the probability of a 1 for any rando in my sample?
0.7.
0.7. So that has a special name, like it's the proportion of 1 values, but it's still the mean. So another way to say this is that what the model's trying to get at is the probability of a 1 for any one person, where that probability would be 0.7 if that's what's in my data as a starting point. Then we bump it up or down based on predictor information. So this is what the transformation is going to operate on. Not the zeros and ones, but the probability of having one that is the outcome the model is predicting. That's what I mean by conditional mean, the expected outcome given your values on the predictors. So if I built a regular regression model to predict the probability that y for each person, by the way, I know it's I for the rest of it, but today it's person. There's too many I's and I didn't want to change them all. So it's people. The probability that y is 1 is what we're predicting in these models. And I can do it with a linear model that looks like this, or linear predictor as it's called. I have my beta 0 intercept. That would be the expected probability of a 1 when all my predictors are 0, just 1 here. Beta 1 would be the change in the probability of a 1 for a unit change in my predictor. And then E would be whatever's left over, what I actually had minus the predicted outcome. So when put together, the model looks like this. So then the question, what could possibly go wrong? With 3 exclamation points, meaning, yeah, there's going to be some stuff that goes wrong. So one problem is this idea that probability is bounded, but the linear predictor doesn't understand that in a standard regression model. So if I have my predictor with a positive slope, the model doesn't do anything to stop the predicted probability from going out of bounds. That's a problem. What we need is for the model to understand that the highest the probability can possibly be is 1 and the lowest it can be is 0. So we need to take that straight line and turn it into this kind of bendy S-shaped line instead. So the linear relationship between my predictor and my probability of a 1 outcome needs to become non-linear as a result. So the effect of x is going to be largest in the middle. The effect of x is going to shrink the closer you get to either of these endpoints. X will matter less. So if we think about this in the context of factor analysis, right? Remember that's this course? That's the one we're in? I swear I remember that, but I got to go through this piece of it. The implication of my factor predicting an item response, let's say that my item response goes from 1 to 5, there's nothing stopping a CFA model from predicting a 6 or a 7 or a 0 or a -1. So if we make it shut off, that makes the prediction stay within bounds, but it also changes how we think about this type of item. If I'm somebody with a trait level out here, this item isn't going to help identify my trait very much. Likewise, if I'm down here, it's not going to help very much. It helps the most in the middle. So this is leading towards the idea that items are differentially useful based on where you are on X, where you are on the latent trait. So how do we fix it? 2-step process. We start with probability. So I have P as an abbreviation for the probability of a 1, 1 minus P as an abbreviation for the probability of a 0. This quantity right here, the probability of a 1 divided by the probability of a 0, that thing is called odds. Like, what are the odds that I'll win the lottery? Like 8 bazillion to 1, something like that. We're used to seeing those sorts of things. It's common in betting and whatnot. So odds is a scale that starts at 0 and ranges from 0 to positive infinity, and it's weirdly asymmetric. So if I have a probability of a 1 of 0.7, then the odds of that happening is 2.33. If I want to describe the probability of a 0 instead, those odds are 0.4. So it's very difficult to think about one as naturally leading to the other because it doesn't work. And in terms of having this be a new outcome to predict, it's better than probability because it's not bounded on the positive side, but it's still bounded at 0. So it's not really continuous. So then some genius figured out that if you take the natural log of this odds, the part between 0 and 1 will stretch out into negative infinity, and then you have something that's symmetric. So this is what a logit is. A logit is, and we have a whole thing we do, the log of the odds of the probability of a 1. You got to commit that to memory. It will make your life easier. Now you're like, what the hell does that do? It creates an unbounded outcome for the model to predict instead. That's what it's for. So for instance, if my probability of a 1 is 0.7, the logit, the log odds as it's called, or logit, of it is 0.846. If I want the logit that corresponds to a probability of 0 instead, that logit is negative 0.846. They're symmetric. So here's a mapping, for example, of how we would go from probability to logits. By the way, in textbooks, you will sometimes see the words data scale or model scale as synonyms for these. Data scale is back on the scale of the original data, like probability of a 1 between 0 and 1, whereas logits is what the model is predicting. So logits are on the x-axis in this picture, probability is on the y-axis, and the table points out a few example values. So the neutral point is a logit of 0. That corresponds to a probability of 0.5. If I have a probability of 0.9, that's a logit of 2.2. A probability of 0.1 instead is negative 2.2. 9.9 is 4.6. Can you guess what 0.01 would be? Negative 4.6. Okay, this is a really, really important point, okay? Here's why. Sometimes your model output will give you parameters that talk about the probability of a 1, and sometimes they will give you parameters that talk about the probability of a 0. To get back and forth, all you need to do is multiply by -1, or what I am told is called take the additive inverse. It's a math term I learned, just for this. Multiply by -1. So logits is what the factor model is going to predict. That way the factor model predictions can keep going forever and ever, but when we back translate those predictions into probability, they stay between 0 and 1. Okay, Zoomers are batting 100 here, batting 1,000. That doesn't make sense. I think batting 100 makes more sense, right, as a batting average? Not very good. No, I'm like as like a percentage. Like if you have 100% like getting on base, like that's the best you can do. I don't know how you can get on base 1,000% of the time. You'd have to like steal or something. That's a different metric. But anywho, yeah, let's do a picture. So I like this picture. I actually stole this from a multi-level textbook on their chapter on how to do logit multi-level models. But the mapping of probability to logits is shown differently here, where probability is on the top and logits are on the bottom. So the point that I'm trying to make is that equal distances in logits, like if I go from 0 to 1 to 2 to 3, do not translate into equal distances in probability. The corresponding distances in probability get smaller and smaller and smaller and smaller. Even though logits can go on forever and ever, probabilities do not. So it's a nonlinear transformation. So going across the 3 potential scales that you could look at your results from, if I have p as the probability that y is 1, then probability ranges from 0 to 1, and the neutral point is 0.5. That's data scale. The intermediate step is called odds, and that is the probability of a 1 divided by the probability of a 0. So the neutral point on that is 1, because 0.5 divided by 0.5 is 1. Logits, or log odds, then take the natural log of the odds, so their neutral point is 0. So a logit of 0 corresponds to an odds of 1, corresponds to a probability of 0.5 of predicting a response of 1. Okay. How are we doing? What's our new vocabulary word? Starts with an L. Logit. What's a logit?
Log of an odd.
Log of the odds of the probability of a 1. Yes, got to commit that to memory. What is a logit for? What's its point?
Transforming binary data so you can work with it.
Very, very close. Transforming the prediction of binary data so we can work with it. Yes, I'll take that. Because we're not actually changing the zeros and ones. Those are actually undefined. A probability of 1 as 1 is logit is undefined, because that would be 1 divided by 0. But the conditional mean is what's being transformed so that we can work with it. Exactly. So that's one problem. So logits are designed to fix the problem of predictions going out of bounds. They make sure that our predicted probabilities stay within range. When we get to ordinal data, logits will also make sure that our predictions stay within the bounds of the scale, like 1 to 5 or 1 to 4, whatever it happens to be, where each integer is discrete. The other issue is about the residuals. So if you have a binary outcome, then you'll get a predicted probability, y hat, from the model, and it's either wrong by this much, getting you down to 0, or wrong by this much to get you up to 1. Like each different predicted outcome has only 2 possible residuals attached to it. That means there's no way on earth that the residuals can be normally distributed. Further, going along with the normal distribution, it only has 2 parameters. It has a mean and it has a variance. A variance being the key idea. It's constant. But in binary data, the variance is a literal function of the mean. It's the probability of a 1 times the probability of a 0. So variance of a binary variable is maximized at a proportion of 0.5, and it shrinks as you move away from that. So that means standard errors for predictions need to shrink as you move away from that. And the idea of one single variance that holds for everyone doesn't work. The good news is that we're not stuck with the normal distribution. The normal distribution is like the one that came in the box, but we can add add-on pieces. We can change it out for a different one, such as our new friend Bernoulli. The Bernoulli distribution only has 1 parameter instead of 2. So here's normal. It has a mean and a separate variance. Stole this from Wikipedia as usual. Here's the formula by which we would compute height. So if we know the mean and the variance for a given distribution, for any person in that distribution, we can compute how tall their data are. And we can do that for sets of outcomes in multivariate models as well. We can do the same principle, but use a different formula for height for binary data. So if we use the Bernoulli distribution, then height is a function of the probability of a 1, if that's what you got, or the probability of a 0, if that's what you got. There's only 1 parameter. Once we know the predicted probability, we know the error variance around it. And it's a different number based on what that predicted probability is. So variance can't be constant and errors can't be normally distributed. But if we say they're not, if we say they're this instead, then it works out just fine. So we switch it out. And this general principle operates across all different kinds of regression models, as well as factor analysis type models. You find the distribution that best matches the possible values of your outcome, and you use a link function to ensure that your predictions stay within the boundaries of whatever your outcome is. So it's like plug and play different pieces. And then you can fit your normal regression, or you can fit your normal factor model. Okay. So here's what the model will look like in different forms. Slide 12 is where we are. The point I want to make to you right now is that this is all the same. Each of these equations is 4 different ways of saying the same thing. And this is part of the reason why IRT looks like bananas relative to other types of models. Part of the reason. The one on the top is my preferred. The logit of the probability of a 1 here is a function of an intercept and a slope. And I can talk about this intercept and this slope in the exact same words as usual. Beta 0 is my predicted outcome when x is 0. Beta 1 is the change in my predicted outcome for a 1-unit change in x. The only catch is that when I say predicted outcome, I have to remember it's in logits. So I'll get something back like, 2.3 is my predicted outcome. Like, whoa, what the hell is that? It's in logits. I know that if it's above 0, that it's closer to a probability of 1. And I know that if it's below 0, it's closer to a probability of 0. But logits are not a directly intuitive metric. If you take the log off, or what math folks would say exponentiate, or what I normally say as unlogit, then you can predict odds as the quantity, and then we have e to the power of the prediction. So e to the logit is how I often say this. This is e, that number, and this is in like the exponent of it. I just write it this way so that it's easier to read. So e to the power of. If you do it this way, the terms all get multiplied together, and that's craziness. The good news is that in IRT land, odds aren't really a thing. They just sort of skip over that. So then that gets us down here. If we take the EXP off and we turn this back into a prediction of probability directly, now we're predicting something that people know. Like if I told you the probability of it snowing tomorrow is 0.3, right? You'd know what to do, right? Probably get your boots out, make sure your car has your scraper on it. Like 0.3 is not 0. If I told you the probability is 0.00003, you'd be like, yeah, I'm going to wear shorts tomorrow. I'll take my chances with 0.00003. Like that's an intuitive outcome metric, which is nice. However, then we get into the problem of how do I talk about these coefficients? You can't talk about them in the usual one unit change kind of language. It doesn't work. So part of the disconnect between what factor analysis and regression look like and what IRT expressions look like is that IRT expressions are almost always written this way. Like you don't see this in regression. You see it this way instead. You see it this way in IRT. If you want to do less typing, then this equation right here rearranges into this bottom one, where the difference is the -1 here. So in formulas that I write in code or in Excel, I often write it this way because it's less typing. So 1 over this. So item factor analysis is going to look much more like the first one because it's written to predict a logit, whereas item response theory is going to look much more like the probability one. But we're still in factor analysis class, I promise you. It takes a little bit of disconnect, but I promise you we're there. Okay, how are we doing? What questions do you have for me? I'll ask it that way.
I have a big picture question.
Okay.
When I hear like CFA or IRT, I'm thinking, okay, we're taking things and making latent variables. Sorry, my brain is. But what I'm confused about is why are they called? But and then you, depending on which one you're doing, is if you have depending on what outcome you're.
Yes, yeah, so let me summarize what you said just far for the microphone here.
Oh yeah, go ahead.
So she says CFA and IRT are when you want to make latent things out of your data, and when you would pick one versus the other is what kind of outcome you have. That's all good. Okay, keep going.
Why are they different? I'm thinking, oh yeah, I would do a logistic regression if I have an outcome, but don't you make your latent traits first and then go run something?
We can't really make a latent trait. It's an unobserved thing.
So it kind of happens within the model.
It doesn't happen directly in the model, but it can be predicted using the results of the model after the fact.
That's what I needed. Thank you.
Yes. I was going to say something about that. I'll hold off on that. Zach has a question.
Sorry if you already said this and I missed it, but so in order to calculate the logit, you would first need to calculate the probability that y is 1 and the probability that y is 0, right? So is there like back-end stuff you have to do before you even calculate the logit?
So for in a regression model, your model would give you a predicted logit as an outcome by following, let me go back to like this, right? If you run your model on your data, so you tell it what x is, you tell it what y is, you say, I want x to predict y, go. It will spit out numbers for what beta 0 was supposed to be, an estimate, standard error, all that stuff. It will spit out numbers for beta 1, and then you can use that to create a predicted logit given any value of x for anyone in your sample. So the order of operations, which I think is actually the next slide, so thank you for that foreshadowing. The order of operations is you create a predicted logit first, and then you can back translate that into probability. So that translation is right here, what's known as, it's called an inverse link function. If you go from logits back to probability, like from model scale to data scale, that's inverse link. If you go from data scale up to logits, that's link. So e to the predicted logit divided by 1 plus e to the predicted logit is how you translate that predicted logit into a predicted probability. Yep.
Which one's model scale? Inverse link is model scale with data scale?
So let me go backwards. So the probability metric, like that's the original scale of the data in terms of what we're trying to predict is the probability of a 1. And that's the version that like my mom would understand, right, if I tell her the probability. But that's not what's being predicted directly. It happens indirectly. What the model predicts directly is the logit scale. So that's why we call it model scale. So to go from data to model is link. To go from model back down to data is inverse link. Yes. And please do not hesitate anyone to have me repeat myself, because I talk fast and this shit is hard. That combination means you bear repetition every now and again. Okay. Other questions or clarifications? Okay. So then here are the rules for what you can and can't do across the 3 scales here. So if I have this model here, I can predict an expected logit for any value of my x predictor. We're going to call that y hat in logits. So I can report that, but nobody knows what a logit is. So I have 2 choices in terms of how I can re-express that prediction. I can take it down into odds, which is e to the power of that predicted logit, and then that would have a neutral point of 1. Or I can take that predicted logit even one further step down into probability. So we have e to the predicted logit over 1 plus e to the predicted logit as the inverse link function. So I can express my predicted outcomes in probabilities, odds, or logits, up to me. The slopes, though, do not have that same flexibility. The slopes in logits, you can exponentiate e to the slope, and software will do this for you quite readily, to create something called an odds ratio. So it is literally a ratio of odds. There's 4 terms in it. It's the odds given one set of predictor values of a 1 relative to a 0 divided by the odds given another set of predictor values, a 1 and a 0. Odds ratios are considered effect sizes in these models. For better or worse, I don't like them. We can talk about why if you're interested, but the good news is that no one cares in factor analysis. They don't like odds either. It's just gone. So I'm on board with that plan. So the slopes, that's the one thing that's the easiest thing to screw up without meaning to. You cannot talk about the change in probability for a 1-unit change in x as a function of a slope. That does not work. It can't work because of this issue. A 1-unit change in logit is not the same unit change in probability. It depends where you are. It's less and less of a change in probability the closer you are to the boundaries. So no unlogiting slopes to talk about probability. The order of operations is compute a predicted logit, then take that predicted logit and put it into probability. All of the pictures that I'm going to show you in IRT unit are going to be in probability metric because they've all decided that that's how it works. And this is how I got there. All right. One more little piece and then we'll be back to our regularly scheduled measurement class. It's one more. Okay. Here is another way of thinking about these things. And I've changed the notation relative to what I had in the generalized class because everyone was confused, so I'm trying to fix it. Another way that people are motivating this use of logit is to pretend. No, pretend is the right word for this, not latent. Pretend. The idea that underneath my binary outcome, there's really a secret pretend continuous one. And the name of that secret pretend continuous distribution is y star. Okay? So then you could say, well, this secret pretend underlying distribution follows a logistic distribution. And here's some pictures of what that looks like, where I would describe it as having a threshold. So there's a point on the pretend distribution where you flip over, right? Because it's like you took a binary, like median split on a continuous distribution. And the point where it flips is the threshold. That's where zeros become ones. And that point corresponds to the probability of a 0. So to make it still predict the probability of a 1, they throw a minus sign in front of it. So intercepts predict 1s. Threshold is what it's called when it predicts a 0 instead. And why you can just multiply by -1 to get back and forth has to do with the symmetry of logits. If I know what the probability of a 1 is in logits, I know the probability of the corresponding 0 has to be -1 times that. So some of the model parameters that we're going to see this semester are going to be thresholds. Some of them are going to be intercepts, and some of them are going to be yet another thing. It depends on your software. M+ gives us thresholds. I truly hate them. And do you know what the symbol in M+ is going to be for a threshold? I know some of you know. Have you seen it before? Vladimir, what's the symbol for a threshold in M+? Do you remember?
No,
You don't remember?
no.
I'll give you a hint. Math is money. It's a $sign. It is a literal $sign is how they index thresholds in M+. Because if you learn this, someone will pay you so that they don't have to. I'm not making this up. It is a $sign. You will see. So I'm setting up why some places do it that way. It depends on your software what you get. But this is one of the choices. Threshold is one choice based on this idea of where it flips over on the distribution. Intercept is from a linear models version where it's predicting the 1 instead of 0. So if I'm willing to say that my pretend underlying secret distribution is logistic, then I can put an E on it. But this is not an E predicting original Y, it's an E predicting Y star, which is why I had to add the star here. This thing doesn't exist, it's just an idea. But if we say, okay, I'll buy that, there's a pretend underlying distribution, that sounds fine, then this distribution tells us what the variance is. It's pi²/3. So you will see this number show up in a whole bunch of different places to represent total variance in models that have binary outcomes. This is where it comes from. Pi²/3 is 3.29. But then someone else came along and was like, nuh-uh, my pretend underlying secret distribution isn't logistic, it's normal. And if you're like, all right, dude, you can have it be normal, that's fine, then that leads to what's known as a probit regression model instead, which is a different link function. So logit is the log of the odds of the probability of a 1. A probit is a z-score. Do you remember back when you first took an intro stat class in high school or undergrad? Anyone have a big, thick book to go with it? And there's a bunch of tables in the book, like on the inside cover. And they had like critical values for different distributions on different degrees of freedom. And I guarantee one of the tables was a p-value in terms of probability to z-score translator. Like you go down the rows and like here's your digits of z and then here's your digits of this way and then you find the p's in the middle, or it was the other way around. That's probit. That table is your probit link function. It is the z-value on the standard normal distribution that goes with that probability corresponding to the area to the left. So a probability of 0.5 is a z of 0. And as you move higher on z, that's a probability closer to 1. Lower on z is a probability closer to 0 instead. And if you're like, why the hell are you telling me this? Because in IRT, probit is called ogive. It is the same thing. And the formula for it has a scary looking integral in it because what you have to do is actually integrate under the curve to get to the predicted probability. So from that motivator, the pretend underlying distribution is normal instead, which means it has a variance of 1 relative to the pretend underlying logistic distribution that has a variance of 3.29. So these are different ways of creating an outcome that is unbounded that we can predict with a regular linear model. However, they are different in scale only. If you multiply probit coefficients or probit predictions by 1.701 to be most specific, then they are very close to what you would get from logits. And this curve right here has a black line and a red line. Can you see the difference? Not very well. The black line was drawn with logistic, and probit was drawn with the red one here. So 1.7 is the link that joins these two. That's how they're different. They're different on scale. So you can think of this as like going from inches to feet or centimeters to meters or something like that. They're the same information, just on different scales. Now, why am I telling you this? Because based on how you estimate your model, you may get a choice as to whether you want logit scaling or probit scaling. But if you are using what is going to be called limited information estimation, you're stuck with probits. You don't get a choice. Probit came first. And then some genius figured out that logit is computationally way easier and gives you predicted probabilities without requiring integration. So then logit came along to sort of be like, hey, this is how we're going to do it more quickly and efficiently. So probits and logits are what our binary factor models are going to be predicting, the logit or the probit of a response of 1 instead of 0. And here's some others that you may have heard of, but that doesn't show up in IRT land very much. Okay, 130. How are we doing? So we're doing factor analysis on logits or probits. That's the big picture. A logit or probit is a transformation of the probability that makes it so the linear model can keep going, but then we rein that back in, and the predicted probabilities stay where they should. All right, question from the Zoomers, Kelsey.
I was wondering why probits are the only ones used for the IFA. Like, is there a specific reason why you wouldn't be able to use logit, or is this something we're going to get to?
The quick reason is because that's what the software does. If you wanted to do logits in a limited information estimator, I think you could theoretically, but software is not designed to do that. The rationale is that having a variance of 1 creates like a standardized metric that's more intuitive in terms of that type of estimation, because it's going to be based on a correlation matrix where the variances are 1 as well, so it like ties nicely together. I'm going to say a few words, and I'm not entirely sure they're correct, but also from what I understand, in terms of Bayesian estimation, probits are easier to work with. I believe you can Gibbs them, whereas logits take a different kind of Metropolis, Hastings, other thingy that's harder. How's that?
You got the buzzwords.
Yeah, I win Bayes. So that I know from my husband and his programming and whatnot, because that's what he does for a living, is write software. And that's not what I do for a living. I really don't want to do that for a living ever. Hi, honey. Yeah, someone's got to do it, and that someone ain't me. But that's part of the reason why I think, like, computationally there are advantages that speed things along if you're dealing with a variance of 1 rather than a variance of pi squared over 3. But you know what? If you're like, hey, my software gave me probits and I don't want that. All right, multiply by 1.7. Fixed. The other thing that I want you to realize why this is here, as you will see in a few text boxes, but not in my primary equations, if you look at an IRT book, there is a 1.7 stuck in the exponent in several of the slides. Does this look familiar? Right? So it's like IRT model, and then there's a 1.7 sitting out in front of it. This is why. Because what that does is make the IRT model predict logits, but the interior, the parameters, are scaled in terms of probits. So then the parameters are in probits, then you multiply them up by multiplying by 1.7, so that then you're predicting the logit scale. So it's just a choice as to what your reference point wants to be. Do you want to say that the underlying variable that we don't have has a variance of 1, or let it be pi squared over 3? And I say pry not, because we don't know what the underlying variable is. It's not a thing. Like, we don't have it. There's no way we can test an assumption related to a piece of data we don't have. And yes, I have actually seen simulation studies that have done this, and I'm like, really? Like, what am I supposed to do about it if my pretend variable doesn't follow the assumed distribution? Like, how am I going to fix that in life? So I wouldn't worry about it, but I do want to sort of tell you why things are the way they are and what's motivating them. It comes from this 1.7 being the translation between logits and probits. ogives, excuse me.
So, really
Okay.
quick, so like, does that mean we can get back to, can we go like the same order of operations to get to like probability from, no?
No, that's the issue. So there is no middle layer of odds because probits have nothing to do with odds. So to get from your probits to probabilities, you have to get like a distribution function like in Excel. If you tell it to use the cumulative normal distribution, it will give you the probability that goes with that z value. Or you go back to your book from Introstat and find it in there. There's probably ways to do various hand calculations to get that, but I'm not about to do a hand calculation in this day and age. So I would use Excel at a minimum, and most software like Margins and Stata, it'll print out predicted probabilities for you. That's what it's doing. So yeah, you don't have to do this yourself. It'll be okay. Okay, back to the regularly scheduled measurement class. So how these things are the same. So we are going to be transitioning into item response theory / IFA because these are equivalent. They are different ways of expressing the same idea. How they are the same as CFA is that they are all confirmatory measurement models. That means we decide how many traits, which items go with them. Do we need any other sources of multidimensionality like error covariances or method factors or stuff like that? We decide. You don't have to be right, but you gotta have a clue to get started. Like CFA, both items and subject, put an S on there for me, I'll fix it after class. Items and subjects matter because their properties are going to be included. We are going to have parameters called item difficulty, item discrimination, and we're going to have subject factor values, factor scores essentially in the equations. Item discrimination is going to be the same thing. It's a slope. So the same concept as a factor loading being a slope holds for these models as well. The slope indexes the strength of relationship where steeper is better. They differ though in how we're going to talk about item difficulty. There are 3 different ways that we can talk about item difficulty: thresholds, intercepts, or what are known as actual difficulty parameters. After controlling for a subject's latent trait, so we're switching notation here to be consistent with how the world does this, F, my factor, is going to be called theta from now on, this symbol. It is a synonym. So we can add this to our list of synonyms. Latent factors are latent traits, are latent variables, are latent constructs, are true scores, are thetas. And in the context of educational testing, I would add in ability, subject ability, to that list. But since some of you aren't looking at ability, you're looking at things like tendencies toward alcoholism, or what's your construct called? Structural racism, right? There's nothing to do with ability in terms of those things. Maybe drinking ability, but I would hesitate to call it that, given that to be really able means you're probably going to die soon. So ability is in the context of educational testing or testing, specifically, but we're talking about a trait as a general hidden thing inside you that we want to try to measure with observed variables. It's called theta for the next month or so. We can still say that the only reason item responses are correlated is supposed to be a theta. However, you don't have to have only unidimensional models. IRT does not assume unidimensionality. It does if you fit a single factor model, but you don't have to. If you think there's 2 traits that underlie your item responses, fit 2 traits. If you think there's 3, put 3 in. So then we would change the assumption to be independent after controlling for all the thetas that are predicting your responses. As in CFA, this can go awry if you have reasons for multidimensionality that are not captured by your factors or your thetas, such as specific factors for test slits. So I think, is Charlotte here today? I don't see her. So one example, if you have students read a paragraph and you have them answer like 5 questions about a paragraph, those questions are probably going to be more related because they all came from the same paragraph, regardless of a student's ability about reading, comprehension. So we got to build that into a model. That is called a testlet, and the way we would set that up is like a bifactor model. We would have a separate factor for each paragraph that captures additional relationships between the items that don't have anything to do with ability and have everything to do with just what this passage was about. So that's a way that we can build in multidimensionality in a planful, expected way so that we can best capture ability, or theta, or factor score, uncontaminated with anything else. The only catch is that it has to be done this way, method factors, in certain types of estimators. So how they're different, then. Link functions. We're doing factor analysis on logits and probits. That's what we're doing. So logistic or probit regression, as opposed to linear regression. The latent trait has a new name, but its slopes are still trying to do the same thing. They're trying to predict associations of the items. But I'm using the word association to be more general, because in categorical data, covariance isn't really a thing in the same way. There's more to the story than that, but just understand that it's the same idea. The model is trying to say, okay, how are the items related in the data? Now, if these items are consistent with measuring one thing, here's what the model says they should look like and how far off are we. That same idea of discrepancy between model and data still holds. Another big difference, though, is this nonlinear slope, the bendy line, this thing. That means that we can no longer think about items as universally good or bad, but they got to be good or bad for whom? The slope will shut off. So in thinking about what an item is used for, we need to know where the slope is strongest at its difficulty level. Is going to be the answer to that. So we're going to have logit or probit as what's being predicted. Depending on estimator, you may not get a choice of that, and we can talk about it equivalently after doing the translation. So this is the big difference here. Straight line or bendy line. CFA is straight line. Straight line doesn't understand where the boundaries are. It goes on forever and ever. But if we say, hey, straight line in terms of logits, we're good. Logits do go on forever and ever, and so do probits. Straight line works for that. But when I take each of these predicted points and I inverse link the predicted logit back to predicted probability, it creates this bendy line instead. Bendy lines, that's the big difference. By the way, these are what are known as parametric IRT models, meaning the bendy line follows a very specific function. There's a whole set of models that are called non-parametric, where it's different kinds of bendy, data estimated bendy. That's the key word if you're interested in those things instead. So the vocabulary then, here's the summary of what these things are called. We have IRT versus IFA corresponds to different ways of talking about the same model, different versions of the parameters. Difficulty discrimination goes with IRT. Loadings and thresholds goes with IFA. The other distinction is how we estimate them. Traditionally, if we use full information, maximum likelihood, meaning we use all of the original responses and we get parameters that tell us about difficulty and discrimination, we call that IRT. If we switch estimators and talk about it using limited information, meaning we start with a summary of the data and estimate the model on that summary, that is more commonly done using loadings and thresholds in IFA. So these words correspond to two differences at the same time. What the model looks like in terms of what the parameters are and how it's being estimated. You can do the other cells though. Like M+ will do all 4 of these cells. And M+ will give you either version of the model for binary data. Lavaan, by the way, only has the last row. It only has limited information for these models. So that's one of the reasons why we need M+ for the rest of this class. So I'm going to start with IRT. And then the next lecture, probably in like 2 weeks, maybe after spring break, is going to show you the IFA version. The reason for that is because I think the IRT parameters are more useful. And they lend themselves much more directly to talking about how we think about reliability. So we're going to do IRT, even though it's going to look crazy different than what we're used to. Can you just bear with me? I promise it's still factor analysis class, even though it looks crazy. You believe me? I can prove it. There's math, I can prove it. No, you don't believe me? You want to see the math? It's actually really easy math, but it's not in this slide deck. So you're going to have to wait until later to see the math. Okay, all right. All right, cool. Questions as we close out our Happy Tuesday Garbage Day?
I have a question about the discrimination and loading. Is the discrimination really different from the loading we have seen in CFA?
The question was, is discrimination different than the loading in CFA? They are going to be a 1-to-1 exact match if the factor variance is 1. If the factor variance is not 1, then I believe it's loading divided by the standard deviation of theta, if memory serves, but the variance is part of the formula in there. But conceptually, yes, discrimination is a factor loading. Difficulty is a whole nother thing, but a threshold is the opposite of an intercept. Intercept times -1. I know opposite is not a good term, but that's how I think of it. Other questions? All right, then I hope to see everyone Thursday. Keep working on homework too, and let me know if you need anything, okay? Thanks for being here. Thank you, Zoomers. Thank you, Roomers. Bye for now.